Let's look at a few examples here. And what I want to do is talk about how system changes might be drawn here. So we're going to focus on system changes, and in particular, these are going to be reversible system changes. So I've drawn on the previous page a picture of a PV diagram. It looks something like this. Probably should have put my axes up there to begin with. And we're going to be moving from an initial point P1, V1 to a final point P2, V2. Now the whole point of the PV diagram is that I could just have a process that does this. State functions like the internal energy will always represent the same quantity no matter how I go from this first point P1, V1 to the second point P2, V2. But that doesn't mean that's how the process had to go. The process could have followed this path to get there, or it could have gone this way to get there. Okay, however it goes from here to here won't affect the internal energy, but it will affect the heat and the work that are involved in that process. And that's why they are called path functions, because these are different paths that took me from an initial state here to a final state here. All right, so what can some of these initial and final state paths look like? Okay, well, let's look at those different change processes with constraints. So remember, an isochoric process was constant volume. Constant volume. So that means if I start here at this point, constant volume is always the horizontal axis. So that means I have to go straight up vertically to my final point. So this would be an isochoric process, would be just a vertical line on this. What about isobaric change? Remember, that was constant pressure. All right, so now if I start here and I go to here, I would have pressure is constant because it's the vertical axis, volume is the horizontal axis. So in the first case, I have this is going to result in a change in pressure. In this case, I'm going to have a change in volume, but no change in pressure. The pressure listed over here is constant. Now I've drawn this as an expansion because the delta V is positive, but I could have also drawn this for a compression where the delta V is negative. All right, so you can represent both of these things on a PV diagram. Okay, what about isothermal? That's the third constraint. Okay, isothermal, remember, was constant temperature. How does that look on this? Okay, well, to see this, we're going to have to rely on our ideal gas equation of state. So we're assuming that this is an ideal gas now. And remember, that's equal to nRT, but this is constant. And in an isothermal process, so is temperature. So in effect, PV equals constant. So what does that graph look like? Well, if I start here, that graph might look like this. It kind of curves down. It looks like a hyperbola. So here is my initial point, and here is my final point. All right, so this would be an isothermal change and how it looks in this PV diagram for an ideal gas. Okay, for a non-ideal gas, it may look a little bit different. We're actually going to be talking about isothermal changes a little bit later and see how we can, what we can learn from looking at the shape of this. Now, I've talked a little bit about how we might represent these paths in a PV diagram, but how do we calculate things? Well, remember we wrote that work was equal to minus P dV, the incremental change in work. So if we actually want to calculate work, we have to do an integration from the initial point to the final point, and it's going to be the pressure times the change in volume. Now, I've explicitly written the pressure here as a function of volume. Okay, as the vertical axis in each of these graphs, we are seeing here that these things, these paths, tell us what the pressure as a function of volume is. Whoops. Let's draw that P as a fraction of volume. Here, P as a function of volume. P as a function of volume is a constant over the volume in the isothermal case. It's a constant as a function of volume in the isobaric case. it's just a horizontal line. Okay, so if we're doing this, what does this integral represent? Well, I hope one of the things that you learned in calculus was that an integral of a function is basically telling you what is the area under the curve. So what I'm really getting from doing this evaluation of the work is I am measuring an area. And the magnitude of that measurement is going to tell me what the magnitude of the work is. Now, I've left something out of this equation. I've left out that minus sign. So what that tells us is if I have a process, I need to multiply that area by -1 in order to get the work. And this is going to affect how we interpret different things in the diagram. Well, let's go to another page and see how we might draw this. So work on a PV diagram and how this would be represented. Okay, so work is equal to the magnitude of the area under the PV curve. P is a function of volume. So let's say, for example, we have an isobaric process and it's an expansion that goes from point 1 to point 2. All right, so P is equal to constant. So this is isobaric. If I did that integral for the work, remember the integral is -1 to 2 of pressure times dV. The pressure is constant, so in this case it's going to be minus the pressure times the integral of dV from 1 to 2, which is just minus pressure times V2 minus V1. All right, so what is that in this case? Well, the area under this curve is just this area. So this would be the magnitude of the work. Now, since it has the minus sign out here, and this was an expansion, that means that this is a positive quantity, and this makes it negative. So in fact, it's going to be the negative of this in this particular case. All right, what if instead I had used as a compression? What would it then be? Well, now it would be the area under the curve and it would be positive. So what this is telling us is if we are moving from left to right, the work is the negative area, and if we are moving from right to left, the work is the positive area under the curve. All right, but this is going to be true for any path that we might follow from an initial point to a final point. So if my initial point is here and my final point is here, and actually I've screwed this up a little bit by making this such a complicated diagram, but for this part of the curve up to here, it'll be the negative area under this part of the curve, and now it will be this part of the curve here and this part of the curve here, but it won't include this region in here because we were going from right to left. So this is a case where it's really the area inside this curve and the horizontal axis. So in general, what we'll find is that if we make some path, and even if we, let's say we make it a path that comes around in a total circle, well, this part of the path will count as a negative work, but it will go all the way down to the bottom. And then this part of the curve will count as positive work, so it will cancel that out. So when these two cancel each other out, we find that actually the net work is equal to the area inside this, and it will end up being a negative area because the higher curve was the one going from left to right. I've probably told you more than I needed to tell you at this point, but what we can see is these PV diagrams are remarkably useful when we want to talk about different kinds of processes that are reversible, so that we can describe the path that connects the initial point to the final point.